So before we start to make the heat map, another point we may be very caution is the missing value problem. But since this hands-on is for heat map, so we will just do very simple missing value imputation. We will select the median value to impute the missing value. If you look at the, okay, again, let's first, we have our dataset CRC, but in order to make the heat map, we don't need the sample information of the last several columns. We only need the protein abundance data. So then that's, you can just, so the first step we do for our dataset is to separate the dataset to two parts. Usually you will have two files. One is protein abundance file, another one is sample annotation file. But just for hands-on, I put them together. So now we need to separate them to, the first one is CRC protein abundance is the first 1 to 72 columns is all the 72 proteins. Let's run it. So then we will have a new file which is only contains the protein abundance data, as you see here. But we also need to keep the annotation information. So then we put all the other columns in a annotation file. So, not this. You see here, the file only contains the sample annotation. So basically, we will use the protein abundance, this data set, to make a heat map. But as we see, we also want to annotate the heat map. Then we need the annotation file. So next step, we just see we need to deal with the missing value. If you look at the protein abundance file, let's just see there are some NA missing value. So in specific sample, the protein, we don't have the protein abundance data. So one way to deal with it is just remove all the samples which has the missing value. As see here, that's the function we can use, NA omit. It will just remove all the rows. Row is our sample patient, which contain the missing value. As you see here, we see after we remove all the missing values, how many columns we have now? We only have, see here is, we only have we only have 89 patients, but originally we have 200. So it's fine. You can continue doing the following cluster heat map based on the 89, but we want to keep some of the samples if the sample doesn't have a large proportion of missing value, right? So then let's see. The first step we are going to do is just we want to know for each sample, for each protein, how much percentage missing value it has. It's just a very simple function. Like for each, here is like given a vector, we will count how many missing values here. Sum is NA will tell us whether the element is a NA. And we want to sum how many, for given vector, how many NAs it has. And then it's the total number of samples, cases in the vector. So this function just tells us how the percentage of missing value in a given vector. Let's see how we use it. So we have our data set, the original data set, protein. Let's first run this row, and I just okay. Here I forgot to mention. Here we define a function in R. In R, you can define a function. If you will repeat using the same code several times, you may want to put the code in a function so that you only need to call the function name next time when you want to use the function. So here we just a very simple function, calculate the percentage of missing value in a vector. Then first thing we want to calculate for each sample how many percentage of missing value it has. Let's see here. We have 200 samples. Most of the samples has low relative. See our samples. Most of the samples has relatively low percentage of missing value, only 1 to 2% of the missing value. But some samples, as you see here, they have more than 5% missing values. So it's all based on here it's based on my past experience. I decide use a 5% threshold. I only want to keep the samples with less than 5% missing value. Yes, we can do the imputation, but if the missing value is too large, too many, the imputation of missing value will not work very well. So we only want to impute the samples which has relatively low number of missing value. So here is I just keep the sample which only. So first we calculate the missing value. Let's run the 62 line. So let's run this line. And then we want to keep only the samples. If you see what is inside it just gives you the index. Actually, we select most of the samples. I think it's 190. We only remove 10 samples. So, and then we only keep the samples, the selected samples. That's the way we only keep it. And next time we have the data set, new data set. What we do is we want to impute the missing value. There are several ways, so there are many ways to impute it. Like the popular way currently in R, there are several packages. I think I found some pages. It's just if you search imputation of missing value in R, there are many solutions about it, like popular R package. Here is just some popular R package, but most of them like math or math something. Actually, they based on the multi-imputation, like the current popular way to do the imputation is they don't impute like a single value for the missing value. They will impute several missing values. So they will generate several data sets. Because in this way, they can count the uncertainty for the missing value. Because why it's missing? Because it's uncertain. So if you only generate one value for the missing value, we don't have the uncertainty. But since it's for this way, you generate multiple missing value, missing the data set, and you will, finally you need to ensemble them at the last step. So since it's complicated, it's not covered in our hands-on. I just use the very traditional simple way to find the median of each, to use the median to impute it. But just to let you know, you can have more options to do it in R. Here, that's the imputation function I write. So actually, it just we use the median value of the observed protein abundance data to impute the missing value. So let's run the whole function. After that, we just have a missing value imputation function, very simple one. Actually, this kind of median mean or median mean imputation function, many packages include it. But since it's simple, so I just write it. And then in this step, we just impute the missing value. after that, if we calculate the missing value again, let's see. Use the new imputed dataset. Here, you will see all the values are 0 because we imputed. But here, just very simple in order to show our later heat map. And then, since you select a subset of samples, we also need to select the corresponding subset samples from the annotation file. Otherwise, the two files will not be matched. So the last row we need to run here. Okay. Now we are ready for heat map. We have a protein abundance, our protein abundance dataset without missing value. We also have our annotation file. We are ready for the heat map. Let's make our first heat map. It's a very simple function in R. It's just a heat map. It's a different. So let's run the line 86. Just very simple. You just tell it the. Okay, that's a heat map we made. Okay, it's quite simple, but we feel actually the heat map is not good. We almost couldn't see nothing. We almost see nothing from the heat map. It's all golden color. Probably there are some dark golden color here, but it's not very clear what happened in the dataset. So we really want to see the different. We want to see something from the heat map. So first thing we want to know is we want to change the color in heat map. But before that, before we do the color skill, we want to just ask some question is, we know, I think probably most of you will know, heat map here, it does a cluster, but what kind of cluster it is doing for the dendrogram. Anyone know what cluster method it is using for heat map? So there are many several cluster methods like k-means, hierarchical, spectral. So idea? No idea? We couldn't only know its cluster. We need to know what cluster, how it works. Then we can know if the cluster not match with our expectation, how should we improve it? So then, just very briefly introduce how the cluster here works. In the slides folder, like GitHub, we have the slides folder. There is a slides called heat. Okay. Hierarchical cluster. It's not made by myself, but just I adjusted a little bit. So let's see, window, view. Okay. So idea is the cluster in heat map. We call it hierarchical clustering. What's the idea of it? It just the algorithm. Okay, it's too complex. But the idea is quite simple. Is we at the very beginning, I think we have example. That's the plot. That's the data set we have. You have several single points, and then you can calculate. So now each point is just one group. As our heat map is one sample, is just one group, and then we can calculate the distance between the two groups. Now it just we calculate the distance between any two samples. So then we find the two groups which has the closest distance. In the plot here, I see we think the closest probably come here or there because they are the closest group. So then we merge the two groups because they have the closest distance. As you see here, it just merged the 2 points here because it's closest. Now we have a new group. In the next step, again, we just repeat the procedure. We keep finding the closest two groups and merge it. See here, the closest one we found is here, and merge it. And then so here is this point and this point are two groups. So we also merge it just quickly, and you will see another closest. Just how it does the cluster. Finally, you will only have one final group because all the samples will have final group. So just remember the procedure. We always find, so we will merge sample group by group. So we will have less and less groups. Finally, you will have only one group. But how we merge the two groups? We based on the distance between two groups. Then we have a question here. Two questions actually. Like the two groups here, how we define the distance between two groups? You have several points here. So we know the distance, like because it's two dimensions, so we know the distance between two groups. We have some method to measure the distance between the two points. But since there are several points in each group, how we define the distance between two groups? That's the first question. That's also the first option we can change in heat map for cluster. Second one, even though for the 2 points, single 2 points, there are several distance. Like we know like a Euclidean correlation distance. What distance you want to use to define the distance, right? So that's a two question, and that's the second option we have for the heat map cluster. And just here, based on our previous cluster procedure, we can just a cluster dendrogram can be made. So, but here we don't. We just give you a final process of merging the groups. Actually, you don't know how many groups in the heat map in the dataset. So it's really it's based on your option. You can just cut the dendrogram from. If you cut it here, you will have 3 groups. And if you cut it in the higher position, you will have 2 groups. So it depends on. It's also so based on your it's based on your selection how many groups. Okay. So first, for define the distance between 2 groups, there are for hierarchical there are 3 ways, popular way. First one is okay. I think I can make some. So if now we have 2 groups and we have some points, each group has 4 points. For the first one, single link, it just find the closest pair. right here. Let's move it a little bit. So it will calculate the distance between all the two pairs, and it found, okay, these 2 points has the distance between these 2 points are the closest. Then that's the distance will be used as the distance between 2 groups. That's the single linkage. And for the second one as the complete, you can also change it in the heat map for this option. The default one, for the heat map, the default one is the second, the complete linkage. How it means, it just contrasts to the single one. We use the furthest distance. As you see here, these 2 pairs, probably the distance between these 2 points are the furthest. So we use this distance as the distance between 2 groups. That's the furthest one. And that's the default of the heat map function. So actually there are some other heat map package in R. You need to be cautious. They have different default function, a default algorithm. Not all of them use the same one. The one I mean complete is just for the heat map, the basic heat map function. So when you use a function, at least you need to know what distance is the default. Yeah, even though they use different distance of different choice for the group distance. So you just at least you need to know what's the default method they're using. The last one is quite simple. It's just to calculate all the distance between all the pairs and make average. It's kind of a trade-off between the single and complete. See, we know because for single and complete, it has they have their own problem. As see here, the same, like we have the 4 groups, and based on the single link or complete link, the cluster is different. So based on the choice of single link or complete link or average, sometimes you will have quite a different cluster. So that's why we feel it's meaningful to try some different choice, because maybe if you try some other one, you may have a better cluster. See the same data, but you will have very different cluster. And also see that's the same data set, but based on the different choice of linkage. See the cluster, that's quite different. Okay. Actually, we can a little bit have some sense of the problem of mirroring, like the closest one. See, it's just like a chain. It's where the single one is famous for the chain effect. It will make the cluster. If you have some points, they are quite close. The points will just dominate the cluster. Because for the single link, it only considers the closest one. Like no matter how the other points in the other points in the group are distributed, it doesn't care. It only cares the closest one. So in this way, the cluster will be dominated by some very close pairs. And like here, you see it's quite chain cluster. That's why sometimes we don't like single linkage. But even the default complete, it has its own problem. If you see here, it considers the furthest 2 points. Then what's the problem? If we have some outliers in our dataset, like it's quite reasonable, not reasonable, it's quite common. We have some outliers. Maybe you just have in this group we have points very far from it, but all the other are close to the groups. But we just only consider the outliers. So that's the problem of the complete one. It's quite sensitive to outliers for cluster. So if you want because it's default. So if you see your data set has some outliers. When you make some previous plot, you need to be cautious. The default complete may not work very well. And the average kind of trade-off between them. I know some function, but not all the functions are using heat map. Some function use average as a default method. Okay, I think that's all the points I'd like you to know before we do the hands-on. Okay. Before we really try to some real analysis, we just see some options. Because for the heat map, as here, the X label is quite messy. We almost see nothing from it. Also the Y label. But since if you have many points or many proteins or samples, even though it provides option, you can make the label smaller. As see here, just use the 6 row, 6 column, but the problem is that even though you make it not overlapped with each other, it's too small. It's still just letting you know you have the option, but it doesn't work very well. You can make it small, but it's too small. Also, for the heat map here, it do the cluster or both the row and the column. Most of the time, I feel like for my research, sometimes most of the time I only interested in one cluster. Like for classification, like we may only interested in the sample cluster, and if sometimes we want to do some feature selection, we may be interested in the protein cluster. So here, just to see, you can tell it, I don't want to do the column cluster. So it will only do the row cluster. That's just some tricks when you use the function. Okay, until now, question? Okay, then let's go to the next one, the choice of the distance. Here, I just want to emphasize two types of distance. Okay. So let's first load a package called BioDistance. BioDistance is a package which just give you some popular distance we use for biological data, like our Euclidean or correlation distance. So let's first load it. Okay. See the error I have because it's not my own computer. So it tells me I don't have the BioDistance. So I need to, if you have this problem, we need to load it. First install it. Let me see. I think. Oh, I think it's a bioconductor. Do you know what is a bioconductor? Okay, so I think it's a bioconductor package. If you go to the reference menu, it just give you different distance experiment, especially because we also heat map the function. It also provides some default distance, but the problem is they don't provide the correlation distance. So we will show why sometimes we care about correlation distance. But this package, as the experiment and the correlation, it will provide the correlation distance. So if you want to use correlation distance, you can use the distance from this package. Also, it's very small. So let's first install it. After install it, let's just load it. Okay. Do you have problem about loading the package? So for the last two hands-on, we still including heat map. We have another hands-on as multi-dimension because we will need to do some statistical analysis. So we'll start to use some package from bioconductor. And every time if you couldn't, you see an error, no package, no such package. Just try to first install it. Okay. Let's first use a toys example to see what's the difference between Euclidean distance, the common distance, and the correlation distance. So first one, we define 3 genes in 5 samples. Let's run the code 104. Let's run gene 1, gene 2, gene 3, and combine it in a matrix and give the name of column and rows. This one given name. It's just a toy sample, and see the sample. That's a data set we made here. So we have 5 example, 3 genes. If you look at the code, interesting is how we generate gene 2. We just add 4 to all the data, the value. So it means gene 1 and gene 2 should have the same trend of between same pattern across the samples. But they have different. Let's make a plot and see how it works. So and then again we need to load the ggplot2, and we use a package to make the required format of ggplot2. So because the dataset we made before is a wide format, it's like one column is that's the matrix we made. It's genes as column, samples as the samples as column, genes as row. But it's not the required format of ggplot2. As we see before, ggplot, if we want to plot gene, sample, and we need a long format. It's like we need a format like gene, sample, and value. So gene 1 in sample 2 may have value 2, and gene 1 in sample 2 we may have value 4. We need a format like this to make the plot for ggplot2. Then we just here. Okay. We first add a new column in E1. Now that's how E1 look. It's gene. We add a new column, and then we make it to long format here. This one just to this command to make the data from wide format to long format. And that's all we learned it yesterday. So now if you see the data set, it will become this format. So for our data, for the many of the R package, you need to change the format from wide to long, long to wide. So then it's because different package require for different formats of the input. Now after we have the long format, we can make the plot. That's a ggplot. We want to X is a sample, different sample. Y is the protein abundance, and we want to make the line for different gene. If you run the ggplot command, you will have plot like this. This plot is quite useful, like in our proteomics community, because as I mentioned, we really need, like for the raw data, especially after we do the peptide quantification, we really want to see for specific protein, for each protein, how its corresponding polypeptide looks like. Then we need a profile plot. As you see, here is different gene, but we may want to make like different peptide for single protein. As you see here, we call it profile plot because we can see the pattern of the profile. So we have 3 genes. If you do cluster, can anyone tell me which genes are in one group? Which genes are in the same group for the 3 genes if you do the cluster? Which one? 1, 3. Yes, based on what? Why you think? Yeah. Because if you use the common distance we use, we just count the distance between them. So we will calculate the distance between the sample. For each sample, we will calculate this distance between them. So if you use just like Euclidean distance, we should expect that these 2 genes are in the same group because they are very far from it. And let's do the heat map and see how the heat map tells us. Okay, let's run 121. So this time, see the distance function. This is the option. You can tell heat map what distance function you want to use. The distance function we want to use is Euclidean, first one. That's the default distance function in most of the software. So let's see, run 121. Okay, that's the heat map we made for this one. So let's see let's just ignore the sample cluster. Focus on the gene cluster. That's why I say for different objective, you should consider different distance. Here, for the gene 1, 2, 3, it put a gene 1 and gene 1 and gene 3 in the same cluster, match with our expectation from the plot. We thought gene 1, gene 3 is quite close. But here is another problem. I also, in my own research, I also came across this problem is, if you look at, let's go back to the previous. Profile plot. Sometimes, especially when we do the feature selection, we really expect, now they are very close, we expect the 2 genes or 2 proteins, they should follow the same pattern. So if one protein increases in such amount, another protein also should increase in such amount, right? So that's for feature selection. That really depends on our objective. For my objective, because I want to do the feature selection, I really want to filter out the protein which doesn't have the same pattern as all the other proteins. So in this case, we need to consider the pattern between the pattern of the proteins, whether they follow the same pattern. If you want to, you are really interested in the patterns of different proteins or genes or even peptides. So most of the time, I think it's peptides. Like for the same protein, we're interested in, we only want, for protein quantification part, we probably only want to keep the peptides which have the same pattern. Because due to our technical problem, there may be some noisy peptides. They don't follow sometimes they just follow just a horizontal line. So we know we don't want to make it, we don't want to use it for quantification. We especially don't want to use it for the following statistical inference. It will influence our statistical result conclusion. So in this case, we want to use the correlation. What's the correlation? Correlation is to consider whether the two proteins follow the same pattern. Let's see if we use the same cluster, if we do the same heat map, but now this time we tell it, I want to use the correlation distance. I don't want to use the Euclidean distance. What is the output? Again, see, this time gene 1 and gene 2 is in the same group. As we saw before, gene 1, gene 2 really, okay, let me make it. Gene 1, gene 2 really share the same pattern. So here, just to give you a sense of what's the difference between correlation and distance, the common distance we use, including Euclidean, but some other like Manhattan. So based on your own objective, research objective, you should select the appropriate distance you want to use for the cluster, for the heat map. Okay. Another thing is actually we want to, but if we do scale, and sometimes when we have a data set, we will do a scale, just minus the mean and divide by the standard deviation. We want to know whether it will influence our cluster. Okay, so first we need another library. Okay. Called gene filter. So here is we want to. So again, there are many functions you can do the scale, the standardization. But I just because it's simple, so we can do it just one command in R to do it. Just minus the row means and divided by the row variance, standard deviation. So now, oh, I forgot. Yeah, we need to elaborate. So after elaborate, because row means is the default function R provide, but row standard deviation is now. So we need the package to use the row step. Let's simply it's just to make the scale. And after that, after the make a scale, let's see if we make the same heat map on the scaled data, what happened. For this part, we just want to consider if we do scale, how our heat map change. So again, let's see, we will make the same profile plot as before, but only based on we run the line from 142 to 146. So we just make the same profile plot. But okay, now this time, see, we couldn't see gene 1 because it's overlapped with gene 2. They're exactly the same after we minus the mean, because they have the only difference between them is just the same 4 distance. We add 4 to gene 1. So after we do the skill, gene 1 and gene 4, gene 2 is the data is the same. So they are all left. So sure, if you do the, let's see, let's first do the cluster heat map on the original data set, but use the Euclidean distance, not correlation. So what happened? Okay, really should. So we know it, we ran it before. It's just the Euclidean distance on the raw data. But now if we run the same one on the same heat map on the skewed data, center skewed data. Okay. Sorry. See, that's the original one. Gene 1, gene 3 is in the same group. But after you do the skew, gene 1 and gene 3 center skew, gene 1 and gene 3 is not in the same group. Instead, gene 1 and gene 2 are in the same group. So what the conclusion we can get from here is, if you indeed do the skew of center, it will change your cluster result. So when you do it, just be cautious. It will influence your output. That's for the Euclidean distance, the common distance. But how about if we do it? How about we do the same thing, but based on the correlation distance? So just a remind this. In summary, is the Euclidean distance is sensitive to the skew and center. But if we do the same thing based on the correlation distance, okay, let's see. So that's our original. That's our correlation do the cluster on the correlation distance. The two, remember what gene 1, gene 2 are in the same group. But if we do it on the center skewed data, what happened? Same, right? It means correlation distance is not sensitive to the skew and center. That's just a conclusion I'd like you to remember after the course, like the message. So that's when you use it, you need to be cautious. Okay, that's for the center and skew part. Yes. So that's the point is here. Actually, the center skew will change, like here. The two correlation distance plus center skew will change the order of the sample. So since the center and correlation is not sensitive to center skew, so my suggestion is, if you really want to do the correlation distance, just do it on the original skew. If you want to do the cluster based on correlation, do it on the original skew, not on the skew centered skewed data. Okay, other question? No? Then let's go to the next part. So I know there are many new concepts here. So another skill. The previous one, we do the skill by ourselves on the data set. But actually, heat map, it has option for skill. But why we couldn't directly use the skill in heat map, the function? Because let's first see the output, and we can go back to why we couldn't use it. So the same original data set. Now we just use the original data set. We use the Euclidean distance here. And we say the default of heat map, they will do skill. The default setting. But now we say we don't want the heat map do the skill. What happened? Okay. Okay, that's our new data set. But if we say the same thing on our previous one, we say we just want to show the influence of the skill option. Now we say first one we want to say we don't want a skill. Second one we just remove it because default it will skill. That's how to see the difference. Can you see the difference? First, like look at the cluster. 1, 3 is in the same group. 1, 3 is in the same group. Cluster, does cluster change? No. So, but in our previous practice, we know Euclidean distance is sensitive to the skill. If we introduce skill, the cluster should be changed. But here, the cluster doesn't change. What changed here is, if you see, the color changed in the heat map here. So the conclusion here is just when you use the heat map function, one point is the skill here, it will not skill the cluster. It just skill for the color. It will not change, even you change the skill option in the function. It will not change your cluster. It will only change the color of the heat map. So if you really want to have some skill-centered data set, you need to do it by yourself and give it to heat map. That's one point. Another thing is, okay. So I think you can also expect it. So if the data is already skilled and you give it to it, so no matter what options you tell the skill, it doesn't change because the data is already skilled. Okay. Run here, one. Oh, I think I changed it a little bit. So does everyone follow with me until now? Okay? No question. So let's run the last part. That's one without skill. If we tell it, I want skill. See, all the color, everything is the same. So if the data is already skilled, so it's not sensitive to it. Okay? So until now, we just use one toy example to show how the cluster, how the skill, how the distance works. Let's go back to our real data set, the CRC data set we have. Okay, let's remember what we feel let's see our original. Okay. That's just a very simple heat map we made on our colorectal cancer data set. We say, okay, we don't like the color because we see nothing from it. Then how should we adjust the color for heat map? Because heat map is quite special. Like in our previous hands-on, we can just change the color brown, based on the R color brown, we can change it to some other color palette. Do you think it will work for the heat map here? Because here we use the sequential color. If we change it to diverging color, do you think it will work better? Okay, let's try some diverging color. Okay, before that I forgot. We need to first library our color. What's the name of it? Sorry. I think we have it before. Okay, here. We need the R color brewer. So I think I don't have the package. Let me see this color. If you don't have the package, just install it. The package is in Quran. What? Okay. Oh, I have it. Sorry. So after library, the package. I forgot the package name. Okay. So after we load the package, we can define our own data color, like the color you like. So I think as Steven also in the color for heat map, he mentioned like one popular color palette is just red, white, blue. Let's try it. So this function will, you can just, as we show in the ggplot2, you can directly select one, I think. Let me go to our, previous colors. Let's see. So you can just directly select any palette from the package. But the problem is, if you select the defined palette, it will have limited number of colors. Like here, it only has 11 colors. But for heat map, we probably need more colors. So then another way to define it for to select color for heat map is another function in it. It's you have a color palette, and inside the bracket you can define any one, like any color palette you want. Here I just defined red, white, blue, and the number here I just tell it how many colors you want. Here I say I want 200 colors because the heat map is. So you can change it based on your data set. Then let's define it. Okay. Let's run the command and see. Then let's run the heat map based on the new color we define. Oh, okay. Let me see. So okay, let's see. What's the output? Okay, that's the new color we defined. Slightly better. Again, we can see something here for the white color. Slightly better than the previous sequential color, but still not very good. We want something better color. How can we do? So that's a very interesting part for heat map. How surprisingly, if you really find the red color, it will look quite different. Let's go to the next part. Is we want to change our color based on our own data set. So based on the range of our own data set. Let's see. Okay. First step, we want to know what's the value range of our own data set. Here, we just run the summary here. If you see, the mean value protein abundance is 6.5. Maximum one is 25. So we want to make a color based on this range. What we can do is you can define how many colors. So colors you want. Here is because heat map provide a quite interesting option. It's here. We haven't run it. Here is you have color option, and you also have break options. How it works is you have a range like if you have 1, 2, 3 in your data set, and you want to have a color for each 1, 2, 3. So just put break here, maybe 2.5, 1.5, 2.5, and then give a color, 3 color, and for 1, 2, 3. That's how it works. Oh, so the color, we just give either to give 1 color because the 2, 1 is transparent. So we only need to give a color like red. So color is always smaller, 1 smaller than the bricks. So that's why we want to just, because our data set is big, we want them to break in, you can set in which value you want okay. So here is, if you set, here is the bricks. If you set the bricks, it means for all the value below it, it is 1 color. For all the value above it, it will change color. So the break is just the point. The heat map will change a color. So in this way, you can just set how many colors you want, and in which point the color will be changed. Like here. So in 2.5, the heat map will change the value. It will change to another value. And then we need to define 2 things: breaks and the corresponding colors here. So first thing we want to see, here we need to to know what's the range of our data. Summary will tell us it, but we want to save it in some. Summary will only tell us the 6 statistics, but we want it more information, like first quantile, 2 quantile, 3 quantile. Like extreme case, you want to color change in every quantile, 1, 2, 3, 4. So the first one we want to know is all the quantiles for our data. If you see the output here, this function will tell you all the quantiles of the data from from mean to maximum. Then we can use this value as the bricks, the color bricks we want to use. So then there are 2 ways to do it. Sorry, what time is it? Okay, I still have time. So many people do is just find the mean and the maximum value of our data set and set the equal-spaced bricks. Like here, you just sequence. Sequence will just give it as mean value and maximum value. It will sequence the data point between them based on the equal distance. That's many people do it. Let's see let's see whether it works. So now we have a bricks here. If you see it, what the bricks, the distance between the bricks it's all equal. It's around 0.5. So here you can also, that's as how many bricks you want, or what's the distance between the 2 bricks. I set 0.5. And then we can select color based on the bricks. Remember, color is always 1 less than the bricks. So the number of colors we want is just 1 less than the bricks. Here is the length of the bricks, and minus 1. And what color we want to use? Here I just directly select the palette, spectral palette. Remember what is spectral color? Okay, I think I close it. It's just spectral. It's the first diverging color in color borrower. So now I know it's first time it's hard to understand how to define the color and bricks, but it really works very well for the following example. So now we have our color, our bricks. Let's define it. Then let's run the heat map on the color and bricks. See, that's the new heat map. We change nothing, just change the color. It's different. But can you see why there are like almost I think 3 or 4 groups of protein colors? Because each row a different protein color. Any idea why the color is so different between the rows? Because some proteins itself is just a high abundance protein. Like the protein abundance is different. Like for the previous one, I think it's just a low abundance proteins, and here the one is high abundance proteins. So in this way, it's hard to see some pattern because it's all we set the brick equally. But if you remember our previous histogram, the distribution of the abundance is not evenly. It's like a normal distribution. Most of the abundance, they just centered in some very small range of the abundance. So then, if we use the eco-spaced color, a brick, it just make the colors. It will only use very few colors because most of the abundance is in that range. What we really want is we should set the bricks based on our content, the data content. That's the next one we will do it. So next one we try to do make it based on the content. So what we want to do is first impute our centered and skewed our data set. Here, center and skew. Now we have center skewed. Why we do it? We want our data set is have minor and positive and negative and also 0 value. So here is it's quite long the command, but the idea is 3 parts. First part is here. For all the value below 0, like below than the mean, we just calculate its content, and so for all the value below 0, we calculate its 0, 10, 20, 30 content. You can change it to more because I use a fewer bricks here. You can set the length to 100. It will give you 100 bricks. But here I only use 10 bricks. That's for all the value below it, below 0. And then we also want a brick of 0. The next one is for all the value bigger than 0. We want another 10 content. So if we run this code, we will have 21 bricks. Okay, let's run it. Let's see what's inside it. So here, it will, let's see, 10 to 0 to 100 for all the value below than 0. And for all the value higher than 0, we will have another 10 countdown. So in this way, all the bricks is based on our data. So it means between two bricks, I need to between the we have brick 1, 2, 3, 4, 5. Like the number between this distance, the number of data points between the two distances are the same. So that's what we want. We want because for specific color, it means two distance between there is one color between them, and there are the color between them is different. So we want for specific colors, for every color, the number of the points with that color is almost the same. So we can see the real distance, we can see what happened in the data set. Then after we define the brick, again we define the color. It's always the same, just the same code. Okay, and then we can make the heat map. See, that's the new heat map based on our defined color. Here is everything. The data is all same. Cluster is all same. Just we change the color. But see, it's much better than our previous, the first version, the golden color. You see here, you can see some, if all the previous heat map, if you remember, it's hard to see just from the color, some cluster. But here, actually, we can see there seems like two groups, the left side here and the right side here. So just from the color, you can see the cluster. Even though the data tell you for the previous heat map, even though the cluster here tell you there are two groups, but it's hard to see from heat map. But if you adjust the color, you can see different clusters from the heat map. So that's why there's some tricks for the heat map if you really want to make a beautiful beautiful heat map. You can also change different color palette by yourself. Next thing is quite simple. Is we know each column is sample. We want to label it. We want to know whether the cluster match with our annotation. But so we should first define. We need to define a color for the bar. Let's see. Now we define a color just based on here, based on our group. So we have 3 groups. We say CRC, we give red color. Healthy, give yellow color. And if it's benign, we give just the blue color. And after we define the color, we can put the bar on top of the heat map. So the same heat map, let's see. Okay. The same one, but now we have annotation, the bar here. But actually, it's really the real data set we just generate our lab participant in the project. So there are some other data sets. Here is for the left cluster. We just see there are more red colors, right? What is red color? Red color is colorectal. But for the benign and healthy, in the left part, it's really hard to. If you see here, it's hard to distinguish them. But for the left side, there are more red color, like colorectal cancer patient. Okay. I think what time? Okay, we have the last part is for color part question. No? Then next part is we introduce, we have multiple distant option, we have a cluster option. Cluster option is just complete linkage or single linkage or average. So there are so many default package default method. We couldn't try all of them. We just select some of them to see what's the different distance. But for our case, you will see it later. They indeed changed the cluster, but I still feel the first one, the default one, make the best cluster. Okay, let's try the first one. Here, heat map. We want to do a heat map based on the correlation distance. Remember, my suggestion is if you want to do a correlation on the original scale, original data. So here, that's the heat map for correlation scale. Compared to our previous heat map, which one is better? Like cluster. That's the previous one, based on Euclidean. So if only compare Euclidean and correlation for the specific data set, the Euclidean works better, give better cluster. But it really depends on your own data set here. And the next thing is we want to see what's the distance between complete, single, and average. We will just see the three one. Our default is just the complete. That's we generated before. It's just a complete linkage. But now we can change it. See here how you change the default, change the cluster methods. You can use a function called hCluster. It will generate a cluster. It just will generate, it will make a cluster. And based on the distance, here you also have a distance. So it have two options, arguments. First, you can tell the cluster which kind of distance I want to use. Second is a method. You can tell the cluster what method I want to use. Here, we just want the distance default is just a Euclidean. So it's just I want to use the Euclidean distance, but use the single linkage methods. And then we have a cluster. Here, we put the cluster in the column here. It just and make it as a dendrogram here. So, oh, it's hard to see it. Okay. Here is a single one. Still, I think single one doesn't work as well as the complete one. Also, as we mentioned before, the problem of single one, the chain effect. Next one, last one we want to try the average. So what we change, it's also Euclidean distance. We just keep the default. But now we make the average. I think average is slightly better than the single one. But still the complete for average, we see basically two groups. Here is the right side and left side. So overall, if you really want, I just for the cluster, I suggest average and complete. Single, you need to be cautious for single one. And here is the last, just to try another distance. It's the Manhattan distance. It's just it's absolute value between the two data points. So let's see it. Now we see we have the distance function, the method we want. See the two methods. One is for distance, another one is for the cluster. Here, for the distance function, I want the Manhattan distance and put the distance we generate on the cluster, and it will give you a cluster based on the complete link, the default linkage. So let's see. For the Manhattan distance, it's quite the cluster it generates is quite similar as as our Euclidean distance. Here I also give you a maximum distance, but you can try it later. I think now it's just the different option of distance and cluster methods. That's almost the last part. Before that, okay, that makes sense so far. Okay. So the last one I just want to mention, there is another function called heatmap2. It's just it's an extension of the heatmap. It has more options, but the default cluster and methods is the same. But it just provides, let's see, the help function of heatmap2. Oh, I forgot. Sorry. Here, I probably don't have the package. Okay, again. That's because here why it looks like this one, because it will provide the density plot inside of each for each column. We should remove it, but here I don't do it. If you look at the help function of heatmap2, but what heatmap2 offer is the color key here and the value key here. Because for the heatmap, the original one, we don't see like what color matching with what value. But heatmap2 offered it. And also in heatmap2, in heatmap, the original one, we can only change the font of the size of the label. But here, you can also rotate the label. But it's not that meaningful. You can still try. It provides here a lot of options, all for the heatmap too. If you are interested, you can explore it a little bit after class. Okay, I think that's all for the heatmap part. Okay, exactly. Good. So before lunch break. Okay, no question about heatmap?
Okay. So we have so many different methods. Which one should we use?
That's really tough.
That's the most difficult part.
Yeah.
How do we choose?
Yes. We try multiple. It's hard to say